Hey everyone, and welcome. Today, we're going to decode what I like to call the digital DNA of computer programming. We're not just going to look at a bunch of code. We're diving deep into the fundamental building blocks. The core ideas that power every single app, every game, and every website you use. So, let's get into it.
So, have you ever actually stopped and wondered what really makes your favorite app tick? Like, what's going on under the hood? Well, it all boils down to just a handful of fundamental concepts. And today, we're going to take a journey from the absolute smallest piece of data a computer understands, all the way up to the complex objects that make all of our modern software work. Okay, first things first, before you can build anything, you have to understand the rules of the game. And believe me, every program, it doesn't matter if it's super simple or incredibly complex, it has to follow a very strict set of rules, just so the computer can understand what you're trying to say. Think of it like this. A computer basically proofreads our code on 4 different levels. First step is the lexical layer. That's just checking, are all the words spelled right? Then you've got the syntactic layer, which is like grammar check. Does the sentence structure actually make sense? Next is contextual, which makes sure your types match up. You can't add a number to a word, right? And finally, the semantic layer asks if the logic itself is sound, to prevent impossible things like trying to divide by 0. So how does a computer actually process all these rules? Well, there are 2 main ways. On the left, you have a compiler, which translates your entire program into machine code all at once, before it ever runs. But on the right, you have an interpreter, which translates and runs your code line by line by line. And that difference is an absolute game changer for finding mistakes. Because an interpreter runs code as it reads it, it can tell you the exact line where something went wrong, which makes debugging so much easier. So once we get the basic rules down, how do we actually think about solving a problem? See, writing code is way more than just getting the syntax right. It's about picking a problem-solving philosophy. Programmers use these different approaches, or paradigms, to structure their thoughts and, in the end, their code. Let's take a quick look at the 4 main ones. Imperative is the classic step-by-step recipe. Functional programming treats everything like a pure math problem, so it avoids changing data outside the function. Logic programming is pretty unique. You just describe the goal, and you let the computer figure out how to get there. And finally, object-oriented, which we're going to dive into later, is all about grouping data and actions into these neat little packages. Think of these as different toolkits, and the toolkit you pick has massive consequences for how you build things. And how massive are we talking? We'll take a look at this. On the left, a simple insertion sort has a complexity of O of n squared. What that means is, as your data grows, the time it takes to run gets exponentially worse. It's slow. But on the right, searching a balanced binary search tree is O of log n. That is ridiculously, unbelievably fast. So the key takeaway here is this. Choosing the right data structure isn't just a minor detail. It's the difference between an app that flies and one that just crawls. This brings us to a really fundamental question. When you create a variable or some data structure in your code, where does it actually go? Let's talk about memory, the physical place where all our data lives. Your program really has 2 main memory areas to play with. On the left is the stack. It's super organized, super fast, and it's used for temporary variables inside your functions. The computer handles all of it for you, automatically. Then on the right, you have the heap. This is just a big, flexible pool of memory for data that needs to stick around for a while. But here's the catch. Anything you create on the heap, you are responsible for cleaning it up yourself. Now, to manage all this data floating around in memory, we need ways to refer to it. And 2 of the most powerful tools for this are pointers and references. And I love this analogy. Think of a pointer as a variable that holds the street address of another piece of data. A reference, on the other hand, is much simpler. It's just a nickname for data that already exists. Let's break that down a bit more. As you can see here, pointers are really flexible. You can reassign them to point to different addresses, and you can even set them to null, which means they're pointing to absolutely nothing. References are way stricter. Once you give something a nickname, you can't change it to be a nickname for something else, and it can never be null. This makes them a lot simpler and, honestly, a lot safer to use in many cases. Now that we have a feel for memory, let's look at a really elegant, really powerful way to solve certain problems. Recursion. It's this whole way of thinking where a function actually calls itself to solve smaller and smaller versions of the same problem. And this, right here, is the mind-bending part of recursion. How do you tackle a massive, complicated problem? You just make a leap of faith. You simply assume that the function you are literally in the middle of writing already works perfectly for a slightly smaller version of that problem. It sounds crazy, but it works. Now, this isn't magic. There's a structured process to it. First, you define your big picture goal. Second, you have to find your base case. That's the simplest version of the problem that tells the recursion when to stop. Third is that leap of faith we just talked about. Assume the function works for a smaller case. And finally, you use that smaller solution to build the answer for your current bigger problem. And here's something really cool. When that recursive call is the very last thing a function does, we call it tail recursion. And smart compilers can actually see this and, behind the scenes, optimize it by turning it into a super efficient while loop. So you get all the elegance of recursion with the speed of a basic loop. Okay, so we've covered the rules, the different philosophies, and where our data lives. Now let's talk about how we assemble all these little pieces into the modern software we use every day. And that's where object-oriented programming comes in. It's all about bundling data and the functions that use it into these tidy packages we call objects. The absolute core idea here is encapsulation. You can think of it as creating a protective capsule that bundles an object's data, its state, together with the only methods that are allowed to operate on that data. This protects it from being changed in ways you didn't expect. And encapsulation enables this really crucial concept called information hiding. So the person using your object only interacts with a clean, simple public interface, commands like enqueue or dequeue. Meanwhile, all the messy internal details, the private implementation, are totally hidden away. The user doesn't need to know how it works, and more importantly, they can't accidentally break it. So where do these objects live? Well, this should sound familiar. It connects right back to our memory discussion. You can create an object as a local variable right on the stack. You can create it dynamically on the heap, or you can use the static keyword to give it a permanent home in static memory for the entire life of the program. And this brings us to one of the most critical rules in languages like C++. If your code allocates memory from the heap, it is your absolute responsibility to give that memory back when you're done. If you forget, you cause something called a memory leak, where your program just eats more and more memory until it crashes. So we've gone all the way from the basic rules of syntax up to complex objects, and it all leads to this final question. What's the real difference between code that just works and code that's truly built to last? Well, the difference is understanding these fundamental building blocks, how you structure data, where it lives in memory, and the philosophy you use to attack the problem in the first place. It's all about building with intention. Thanks for joining me.